So this is the Wikipedia entry for the superformula, and you can see here that there are a lot of parameters that we can play with. So the example image on the right is showing you the different shapes you get based on the different parameters you enter into the equation. So we've got N1, 2, 3, M, A, and B are all parameters we enter in, right? Our user can play with those. And what we are feeding into the superformula is an angle. And they're calling it phi, I was calling it theta, same thing. We're talking polar coordinates here. You feed in an angle, and it's going to spit out a radius. And what that means is, and I can draw it here for you in Sketchbook. So we've got our circle here, just like before. And what we're going to be doing is essentially to generate the shape of that the superformula is expressing. We're going to walk along this circle at fixed angles. We're going to divide this up depending on resolution, and for each point we're going to have an increasing angle, right? So this right here, for this point, we'll say this is 0, 1, 2, 3, 4, so on, right? You get the idea. This angle right here, this they called it phi, so we can go ahead and call it phi, is going to be fed in to the superformula right here. So we're going to feed in phi. We're going to calculate the sine and the cosine with all these parameters and the exponents and all that goodness, and it's going to kick us back out that r value, the radius, right? And it'll tell us how far out to move at this angle, and then once we enter that new bigger angle, it'll give us another value and another. And so these could be increasing, decreasing. Once we've set it up, you'll get to play with the parameters and get a sense of how the parameters control it. But hypothetically, it's generating some sort of radial symmetrical shape like so. All right, that drawing is just beautiful. And that is the gist of it. And so really step one for us is going to be making sure that we can generate points along the circumference of this circle first. And once we've got that down nice and tight, and we've got everything expressed in polar coordinates, we're going to then feed in that angle phi into the equation and get back the new radius. And that'll allow us to draw our shape. And after that, I will show you really quickly a fun extension where essentially we wrap our whole formula in our for loop that generates these points along this circle inside of another for loop. And in that outer for loop, we'll vary the parameters of the equation. So we'll be generating multiple superformula at once, and the resulting image is pretty cool. So let's do that now. Alright, let's go ahead and switch to the technical. I should always be doing this, but sometimes I'm lazy and I don't. And we'll go ahead and throw down some geometry. And we'll call it Superformula 2D. This is the 2D superformula. And we will start off with a null, and you will see why in a second. Because we're going to use a wrangle node, but we're going to use a new one. So before we were using the point wrangle, which was running our VEX code in the surface context, right? the SOP context. We're going to use the attrib wrangle, which gives us a couple more options. It's a little more low level. So internally, if you were to dive inside here, you'll see that it's an attrib VOP, and that means it's running in the CVEX context. So if we were to dive inside here, this is actually the CVEX context. And the advantage of using the attrib wrangle is that we can directly create geometry in the CVEX context. Unfortunately, because we're starting with nothing in this scene, it's throwing up an error. So we're going to trick it with this little dummy node. If this connection is good, it won't complain. So we'll just call this dummy null. And I'm just going to highlight that. Beautiful. And we will call this attrib wrangle Superformula. Dusty. All right, and we're not going to use the group parameter here. I'm just going to lock it so I don't accidentally type anything in there. It won't affect anything now. And we're not going to run over points. We have no points to run over. We're going to set it to run just one time. So the code in here is not going to be multi-threaded or anything like that. It's just going to run one time and generate the points for us and place them. Even though it's not multi-threaded, it will be very fast to create these points and to place them. So that is the power of VEX. And let's begin with just generating a circle on the X and Y plane right here. And we will do so using polar coordinates. And let's first off put a limit on the number of points we use to construct this circle. So we'll call it segments, and we'll set it equal to 100. And now we'll loop over these with a for loop, and we'll store the result into I equals 0 from 0 to the number of segments. And each time through the loop we'll increment I. This is your standard for loop, just like you'd have in C or any other language. And we need to place the new point using polar coordinates, and to even create that point to begin with, we will use two new functions. The first one I have over here in the documentation is add point. So in the CVEX context, we can call this function. If you were to use this in a normal point wrangle, you're going to get nothing, nada, zero, zilch. And we're going to use the second form of the function here. We're going to pass in a geohandle, which in this case there's no geometry coming in, so it would just be 0. But we will call the second function that I wanted to show you, which is geoself. So essentially, we're adding geometry to our self, which we know in this case will be 0. But nevertheless, it's a good habit. It's a good habit to have. It's always called geoself, and we're going to actually use the second form of the argument here for specifying the position we want to create this point at, and we will call it position will be the variable. So vector position equals, and I'll write this a little verbose just to make it clear to you guys. So right now we're just going to create it at the origin. So this should just create 100 points right in the middle. And if I were to middle mouse on this guy, yes, we have 100 points, and they're all right there overlapping. We turned on point display, yeah. So to place these guys, we're going to need to know, we know how many points we have. So we've got 100 points going around this circle right here, right? And we also know that a circle, in terms of radians, in terms of the total sum of all these 100 angles needs to equal 2 pi. I can write that a little better. 2 pi. So, because that's the number of radians to get all the way around the circle, right? And so that'll be 2 pi is roughly, 6.28318 something, blah, blah, blah. And that's, in other words, our angle is going to be this number divided by 100. So we'll take 2 pi divided by segments, and that will give us the phi angle in radians. All right, is that clear? We have 100 points around here, so we're dividing up a circle evenly into 100 steps for each phi, and because it's 2 pi radians to go all the way around, that's how we get this number. So let's go ahead and store the step size. Whoops, we don't need to calculate that inside the loop. So we'll do step equals 2 pi, and well, I'll just write the actual 6.28318. 428 318 divided by segments. And that'll be the actual step size. And each time around the iteration, we'll increase the angle, and we'll call that phi just like they did. And we'll start it at 0. So every time we go through this loop, we will increase phi by the step size, and that will take us a little further around the circle. So at the very beginning, and what color haven't we used here? Maybe this one. So we are going to start out with a phi equal to 0. So that's going to keep us right on this line, okay? And we're going to take 100 steps, and each step is going to be, we're going to add this angle, right? Which we calculated down here. So we'll just keep adding it, and it will keep turning us around the circle. So polar to Cartesian. Can't even spell. Sorry about that, guys. I do not spell. Is position dot x to access the x, because remember we're on the xy plane, so we're not gonna touch z. And position dot y equals, and if you remember from our previous example, bring this back up. Hopefully I still have it. Yes. X equals r times the cosine of theta and r times the sine of theta. But we can also use phi. They chose to use phi. Doesn't matter. Whatever Greek letter you want to use for the angle. So cosine of the angle times r is going to be our x. So in this case, we're going to leave r at 1 for now, too. Oops, not entering. So we'll just do 1.0 times cosine of our angle phi. And then down here, 1.0 times sine of our angle, which we're calling phi as well. All right, so, and I'll bring this up to make it a little bit easier to see. And there is our circle. So, in summation, what we did is we took 100 steps, right? And each step was the angle to go all the way around the circle in radians, right? So that's 2 pi radians divided by the number of segments. So that got us the angle to each one of these guys. And each time through the loop, we just iterate that angle and create a new point. So that gives us, and if we turn on point numbers, you will see 0, 1, 2, 3, 4, 5. It iterated the circle in the order and in the direction that we expected, which is awesome. And now all we've got to do is start passing phi into the equation for the superformula, and it will start displacing these points in the direction we want to go. The radius, which we'll call r right here now, we can go ahead and call it r, will no longer be 1. So we will be calculating that. I could write it up here, equals 1, but really it's gonna be changing. It's 1 for now, it's constant for now, but once we enter the formula, it will be variable. Let's bring in the superformula again right here. So I think what I'm going to do first to tackle this problem is go ahead and create variables for all the parameters, right? So that's the only other thing we need right now to calculate this. So let's go ahead, and those are all going to be floats. And let's go ahead and put them up top, because essentially they're going to be something eventually we want to create interfaces for, float sliders and stuff like that. But so let's go ahead and do float A, we'll set A to 1, float B equals 1. We have the M parameter. What's a good value to start off with here? 3 in the example. And then we've got the n1, 2, 3. So n1 equals, so So 5, 18, 18. Okay. Just gonna copy this guy. All right, so these are all your controls for the superformula, the generalization of the superellipse. And aside from segments, which will control the resolution of what we're generating. And looking again at the formula, let's go ahead and tackle the cosine term. So that should be no problem. And I'm going to actually pull out position from here. Only declare that once outside the loop here. And I'm going to bring this into my text editor so you guys can read it easier. And in addition, we will also have syntax highlighting. Well, certainly better syntax highlighting, I should say, than all right. So, Superformula 2D. This is actually where it is calculated inside the loop, and it varies based on phi, which is why it has to be here. And first we'll tackle, so we'll do m times phi divided by 4, pass in the cosine. M times phi divided by 4. Now, according to order of operations, the multiplication should happen first, but I'm going to be explicit, and we'll take the cosine of all of that. We'll call it the or not. I'll just call it C, because it's the cosine side of it. And all of that divided by A, we take the absolute value of that, and we raise it to the power of n2. We can use the POW function. All right, so these things, we set this to the side, should now be equivalent, right? So m times phi divided by 4, cosine of all of that, and did I get that right? Yes. Cosine of all of that divided by A, take the absolute value of that, and taken to the power of n2. And the other term that we add this to, the sine one, is the same thing, but it's going to be b and n3. So let's go ahead and duplicate that. Oops. Let me make this. Okay. So let's go ahead and we'll call this one, make it S for sine. And this is simply going to be n3, and this one is going to be b. And I think that's all we're going to need. And we can calculate r, which we don't need it here anymore. R is going to be equal to everything C plus S, and this both of these added together. And that's all going to be to the power of a negative, oops, let's do the power function. So C plus S all to the power of a negative 1 divided by n1. So it's this exponent over here, just on top of everything else. And that gives us the radius at the current phi. So that should be good. Actually, that is sine, not cosine. Some of you might have caught that as I was doing it. I was just lazy in duplicating that line. So there we go. This should now execute a superformula for us. And the initial values, the A, B, M, N1, N2, N3, are the same as the first one in the example on the Wikipedia site. So they had values 3, 5, 18, 18. That's what we have as well. And they're assuming A and B are both equal to 1. So we should get this shape. And it's just going to be points. It's not going to be connected. So, which is fine. And let's throw this bad boy down. Oh, glorious. That's exactly what we wanted. We've now implemented the 2D superformula. And I was going to save adding interfaces till the next class, but I guess I can give you guys a sneak peek. So if you wanted to expand this on your own time with some controls, for example, for let's go ahead and do the N1 parameter. Let's go ahead and edit parameter interface on the wrangle. This is how we do it in a wrangle node. Let's throw down a float value, and let's call it N1, just like our variable we're going to be controlling. You can even give it a range if you want. All right. Let's go ahead and set that value to 5.0. And to access that from within here, we can use the VEX channel function. We can read that in as N1. We don't have to tell it where it's. We don't have to give it like some path or anything. It knows that it's referring to this node. So, and now we'd be able to vary the N1 parameter. And you can go ahead and generate these for the other ones. Or CH is what you use for accessing floats. You can also say CHF. If this was an integer channel and not a float, you'd want CHI. If it was a string, you would want CHS. So there's a whole family of functions for accessing channels which work very well with wrangle nodes. How you create interfaces is a bit different for your VEX OTLs and your VOPs. With VOPs, you can promote interfaces. It's very easy. With pure VEX, you have to write them with pragmas, so it won't be as easy as just creating a float slider and querying it with the CH function. So let's go ahead and demonstrate the extension of this I really like, which is what we're going to do is we're going to wrap this function right here, and we're going to generate permutations of the parameters. All right, so let's go ahead and copy this bad boy so we can do our modifications to them. Call it Superformula 2D evolve. And we've got all our code here. And I'm just going to create a new document. Set my syntax to VEX. Much easier for you guys to see this. And we're going to wrap this whole thing in another loop. So basically, in this outer loop, each time we're going to create a new superformula. And each time through the loop, we're going to vary some parameter. A and B are good candidates, but there's no reason why you couldn't vary other parameters as well. It's really up to you how you do it. So let's call this, let's call it, I think I did O in the original. So we'll start at 0, 0.0. I'm being explicit because it's a float. And I think, what did I take it to? 0.5, something like that. I only know this from experimenting with the values. All right, and each time through the loop, we're going to add a small amount. So essentially, this is going to run, 50 times? Yeah, 50 times. So before the loop exits. And each time through the loop, we want to vary A and B. So we can add this. We can add a little bit to A and a little bit to B. And that would just be O. And we can make the O value here different too. So we don't have to add the same amount. So we can multiply it or divide. And this is essentially what the more advanced version of the superformula is that I've been playing with. And if we slot it into here, we will get an error, which is great. So invalid context name. That is coming from, that is because we forgot a curly bracket. That's why it couldn't. That's a good sign too that you have a very basic syntax error when it doesn't give you a line number. But this is the evolving superformula. Very cool. And you guys should definitely play around with these parameters and see what you can get out of it to create a sort of like interesting 3D effect and rendering that I was doing. Well, first of all, we should scale this bad boy down. We could add in a scale parameter, but let's try starting this off smaller. What do we get? Oh, that's very interesting. To get my my cool image, I was not only generating a very high-res superformula, but kick these back up. Fractional M value. Oh, cool. Not only was I generating a very high-res superformula, but I was doing stuff like coloring the points, and I was giving it a little bit of depth. So it wasn't a true 3D superformula, because there is an extension of the superformula in spherical coordinates. So this is all I was doing. I just copied this node in from the original scene. So this is just your normal point wrangle node. And because this is centered, this cool shape here, it's easier to see on this one, is centered at the origin. What we can do is we can take the distance from the current point to the origin, right? And we can then apply the power function to it, which will give it a sort of nonlinear scaling effect. And we're using that to set the z position. Likewise, we have the this bounding box function. This is the relative bounding box. So no matter how big our geometry is, everything's going to fit inside a 0, 1 box. And we're using that to set the color. So we're getting its relative position. So a point in the middle of the bounding box is going to have a value of like, 0.5 or something like that. 0.5 on the x, 0.5 on the y, 0.5 on the z. And that becomes the color, which is essentially gray. So this is just like in the, if you played with I can throw down a sphere, you'll see it better. So if we had a sphere over here, let's go ahead and set it to polygon, crank it up, drop down a color node. If you've ever done this before with the color node, this is kind of equivalent. If you set the color to bounding box, let's go ahead and turn off wireframe. You'll see that the red, green, and blue colors are based on the relative bounding box. So no matter how big I make this sphere, no matter what I do to the radius, the colors are consistent. So it's relative, not absolute value. So we just did the same thing using the wrangle node. And additionally, for rendering purposes, I'm giving each point a random normal. So this is your random function. It's wrapped in a function that says vector, so it's just letting the random function know that it needs to return a vector because there's more than one type. This goes back to the function overloading we discussed in the introduction. How you can have multiple types of the same function, and it's not always obvious to the VEX compiler which one you need to return. So that's why it's wrapped in the vector function. And then I have a fit 0, 1 function to fit the normal in the range. -1 to 1, so for those random values, because by default the random function is going to give us 0 to 1 range, and what we really want is our x, y, and z coordinates potentially point in positive or negative directions. So we're taking it from 0 to 1 range to a -1 to 1 random range, and all of that gets normalized. So a lot of stuff happening in that one line right there, essentially just to get random normals. And if I turn on the normal display, you can indeed see that that's what we are getting. Last but not least, just a random scale and fitting it in a range that happened to be good for the scene I was rendering. So that's all I did, and I will go ahead and give you guys the full scene that has the camera and lights and stuff in it, because it is pretty cool. So all I did was drop down a light, place a camera somewhere attractive, and turned on depth of field to get something interesting out of it. So in fact, let me grab the original scene here for you guys. If I jump back up, VEX and Houdini, week 1, scenes, Superformula, discard and open. All that work gone. This is the original one. So this is just the node you saw me paste in. Let's go ahead and go to the camera view. Nice. We have one area light, one camera. Camera has heavy depth of field on. So we can go ahead and render out of that camera, make sure everything's good. Bingo. Let's see what we get. So this is just glorious point rendering in Houdini. And the effect of this sort of iterated Superformula with the intense reflections and depth of field makes it feel miniature, and it makes it feel like the light is glistening on the droplets of dew on a spider's web. But really it's all mathematical formula, polar coordinates, and a generalization of the superellipse formula. So it's a very nerdy thing, but the effect is very artistic and very cool. So that's it. Hope you liked it. Next up is Philotaxis, and then we are done for this week.